Hi, I'm Kyle, and in this lab, I am modeling a falling slinky. You can click the link to look at the video in which a slinky is dropped, and miraculously, the bottom of the slinky remains stationary while the top of the slinky falls, and then finally, when the top reaches the bottom, the entire slinky falls together. I'm using Python and physics to explain why this happens. The physics concepts used were Newton's second law and the spring force. The reason why the bottom of the slinky stayed stationary was because there was a tension force pulling the bottom up, which canceled out the gravitational force. Um, the center of the mass is moving down and the slinky is being compressed at the same time. And so to the human eye, it looks like the bottom of the slinky isn't moving, but it actually is relative to the center of mass. It's getting closer to the center of mass, but because the center of mass is falling down, it looks like it remains stationary. And so the top and the bottom are moving towards the center of mass, and the center of mass is moving down. As you can see in this diagram, the middle sphere represents center of mass, the top represents the top of the slinky, and then the bottom represents the bottom of the slinky. As you can see, F gravity pulls the center of mass down, while force 1 and force 2 pull the top and the bottom closer to the center of mass. Now let's look at the motion of the center of masses. The blue is the motion of the center of mass, and then the green is the top, and red is the bottom. As you can, excuse me, as you can see, the center of mass's graph looks like it's in free fall, while the top is parabolic motion, which means the main force acting on it is gravity. And as you can see, the bottom is stationary until the top and the center of mass are pretty much the same slope, and that's when that represents when the top comes and meets, and so the slinky is fully compressed, and that's when the bottom starts to fall with the top. In the experiment, the professor also tried something where he attached a tennis ball to the bottom of the slinky, and he asked, what if the tennis ball is attached to the bottom, what would happen? And the same thing happens because the tennis ball is attached to the slinky, and if you treat the slinky as a system and the tennis ball is just one part of that system, then it works the same way as if the tennis ball wasn't there. The only difference is the slinky is now stretched a little farther. For the Python code, I made 3 masses to represent the slinky, one for the top, one for the center, and one for the bottom. And for each mass, I determined the distance between its nearest neighbors, and then from the distance you can calculate the compression, and with that the total force will be the sum of the forces from the 2 springs connected to it plus the gravitational force. And the mass on top and bottom only have 1 spring. And after finding the force, you can use Newton's second law and momentum. And with momentum, you can find the new position. And then you just run that through a loop. And that will model the motion of a falling slinky in Python code.